Alright, we're back into solving equations. We looked at a variety of equations in the first video. We're going to look at some different types here in the second video. The equations that have the quadratic look. Now, what does it mean by the quadratic look? Well, a quadratic equation in your Algebra 1 and Algebra 2 days was something in the form like ax squared plus bx plus c is equal to 0. You had three terms. You had degree 1 here in the middle, you had degree 2 here in the first term, and then you had a constant term when you had it written in descending order. So we have that look, and as you can see in this equation, that's the look that I'm going for here. Notice here are three terms, constant term. This is cosine of x to the first power, this is cosine of x squared. So instead of x squared and x, we have cosine squared x and cosine x, but it has that look of a quadratic. Now we solve a quadratic equation in different ways. We can hopefully factor it, or we can use the quadratic formula, or we can complete the square. So what I'm going to do here is I'm going to see if I can factor this, because I find that to be typically the most efficient way to solve a quadratic equation. Now if it helps you, make a substitution. I don't normally do this, but if you wanted to say let u equal the cosine of x, since this is cosine squared, this would be u squared. So I'd have 2u squared minus cosine x minus u minus 3 equals 0. Now I can factor that, and I can factor it with a 2u and a u, and it looks like I need a minus 3 and a plus 1. Well, I'm going to factor this in a similar manner. I'm going to break this down into two binomials, set equal to 0, where I have, instead of 2u and u, I have 2 cosine x and cosine x. And then I have, notice here, the minus 3 and the plus 1. I have the minus 3 and the plus 1. This would be plus 2 cosine x. This would be minus 3 cosine x, gives me the minus 1 cosine x in the middle. We do a lot of substitution where we let u represent a function of x, and it's called u substitution. And the best part about it is when you write it out this way, you can say u equals cosine of x, or you can say u is cosine of x and get away with it. Not too often can you say u is. Now in this case, I have two factors whose product is 0. So using the zero product property tells me that 2 cosine x minus 3 is 0, or cosine x plus 1 equals 0. In this case here, I'm going to solve this. I'm going to add 3 to both sides. Just kind of overkill here just a little bit. 2 cosine x equals 3. Divide by 2, cosine of x equals 3 halves. Now, you may look at this and say, well, I don't remember 3 halves as being on the unit circle. Well, you better not have 3 halves on the unit circle, because remember cosine x, the range is between 1 and negative 1 inclusive. So this is too big. So this does not offer us any solutions. Now over here, if I subtract 1 from both sides, and again, remember, restricted domain here, or restricted replacement set, x has to be between 0 and 2 pi, including 0 but not 2 pi, then I'm thinking, okay, when is the cosine of x equals negative 1? Well, that happens at pi. And that would be my solution, or if they ask for the solution set, I would write the set pi. Now notice here on these examples, I'm just going for the restricted domain here for right now, but you could expand this for general form for all real numbers. Now this guy here has also got the quadratic look, although it doesn't have a middle term. Now if you think about it, again, if I let u equal the cosine of x, this would be, u equal the cosine of x, this would be 4u squared minus 3 equals 0. Well, it's not a difference of squares, because 3 is not a perfect square, but you could use the square root property. Add 3 to both sides, divide by 4, and then take the square root of both sides. So that would give me the absolute value of u is equal to, well, this would turn out to be the square root of 3 over 2, because you can take the square root of 4, drop the u, or drop the absolute values around the u, you get plus or minus. That's exactly how I'm going to approach this problem. I'm going to add 3 to both sides. I'm going to divide by 4. I'm going to take the square root of both sides. Now, when you take the square root of something that's squared, and we don't know if that something's positive or negative, we slap absolute value bars around it. So I get the cosine of x is equal to, now the square root of 3/4 is the square root of 3 over the square root of 4. I did it just a second ago. That's the square root of 3 over 2. I drop the absolute value. I pick up the plus or minus. Now remember, I'm restricted here between 0 and 2 pi, but I'm going to have positive square root of 3 over 2 and negative square root of 3 over 2. That's going to occur in all 4 quadrants. So I'm going to have 4 answers here. I'm going to have x is equal to pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Now, you get Mr. Calculator out to do this, you're going to get a bunch of decimals, and I'd much rather have an exact answer on these kinds of problems. Everything's been working out very nicely. I haven't had to use a calculator yet. And again, we can write this as a solution set if we put it in the braces. And there are my answers. Now, I haven't really emphasized checking my answers, but because there are some values in which you might end up with 0 in the denominator because you have tangents and cotangents and secants and cosecants, I need to be checking my answers a little bit more readily. Everything I've been doing so far right here has been in cosines. But let's go over to here and let's look at this problem that has a cotangent in it. Your first thought might be to divide both sides by the cotangent of x since you have a factor on both sides. But you'll lose solutions that way. So don't divide both sides by the cotangent of x. Subtract the cotangent of x from both sides. And then factor the cotangent of x out. Now you have two factors. I have this one. I set the cotangent of x equal to 0. Or I set cosine squared x minus 1 equal to 0. And again, I could use the approach I did here with the square root property. Write this as cosine squared x equals 1. Cosine of x is equal to plus or minus 1. I kind of skipped a couple of steps there. Now, when does this occur? Well, let's start over here. The cotangent of x is equal to positive 1 or negative 1, and here at 0 and at pi. It equals positive 1 at 0 equals negative 1 at pi. When is the cotangent of x equal to 0? Well, remember, cotangent is the the cosine of x over the sine of x. It's the sine of x. Gosh, I just said it. It's the cosine of x over the sine of x. And that's equal to 0 when the numerator is equal to 0. Well, when is the numerator equal to 0? Well, the numerator is equal to 0 at pi over 2 and 3 pi over 2. And it looks like I have 4 answers here. Now, you have to be careful. If you were to take these 2 answers and you were to substitute them back into the original equation, it looks like I have 4 good answers. Look what happens when you plug 0 in here and in here. You have the cotangent of 0, which is the cosine of 0 over the sine of 0. That gives me 0 in the denominator because the sine of 0 is 0. Well, that can't happen. I can't have that expression. It's undefined. So not only is this one no good, this one is no good because if I plug in pi, the sine of pi is 0. So these are extraneous. I need to check my answers. Over here, though, if I plug these in, I'll be fine. I'm going to get 0 equals 0 on both sides. I have 2 good answers right here. Check your answers, especially when you have factors contained in the variable on both sides of your equation. All right, now this guy is a little different even more. This guy is a little different even more. This guy is a little bit more different. Anyway, this is unusual in that I have a cosecant squared x and I have a cotangent of x. Now here I had a cosine squared x and a cosine x. I kind of had the quadratic look. I don't have the quadratic look here. However, I do have some identities and some properties where maybe a substitution will make this a little bit easier. You have 3 Pythagorean identities. You have sine squared x plus cosine squared x equals 1, tangent squared x plus 1 equals secant squared x, and you have 1 plus cotangent squared x is equal to cosecant squared x. Oops, cosecant squared x. Got to get that extra c in there. Now, notice here I have a cotangent of x. I can put this in terms of sine and cosine. But look right here. I can make a substitution, plug this in for cosecant squared x. 1 plus cotangent squared x minus 1 equals cotangent x. Now it's in terms of only cotangent of x. That's a big advantage. So you say, well, when do I know to look for that? Well, you know to look for that if you remember sines and cosines go together, tangents and secants go together, and cotangents and cosecants go together. So if all those pairs of trig functions that go together, if one's to the first power and one's to the second power, in your equation you might be thinking about some type of Pythagorean substitution, Pythagorean identity substitution. Now the ones cancel here. I get cotangent squared x equals the cotangent of x. I'm not going to divide both sides by the cotangent of x. I'm going to factor that out. I have the well, I have to bring it over to the other side first. I'm going to subtract the cotangent of x from both sides, factor out the cotangent of x, and I get the cotangent of x equals 0. I get the cotangent of x minus 1 equals 0, or the cotangent of x is equal to 1. Now remember, what I'm looking for here is remember cotangent, I just had it a minute ago, is cosine of x over the sine of x. So when does it equal 0? Pi over 2 and 3 pi over 2. We discussed that before. Again, restricted domain here, restricted replacement set, I should say. And when is the cotangent of x equal to 1? Well, cotangent's cosine over sine. Cotangent's positive in the first and third. So it's equal to 1 when the numerator is the same as the denominator. Well, that happens at pi over 4 and 5 pi over 4. Now you should go back and you should substitute these in to this equation to see if all 4 of these answers are good or if any of them are extraneous. And if I'm not mistaken, it's been a while since I've done it, but if I'm not mistaken, I think all of these are good because I know this has got a denominator of sine just like cotangent's got a denominator of sine. It's not going to be a problem here. It's not going to be a problem here getting 0 in the denominator. It looks like I have 4 good answers. Here it might be a good time to use my set notation. I like to put them in order, so I'll put pi over 4, pi over 2, 5 pi over 4, 3 pi over 2. I like to have the numbers increasing from left to right when I can. If you left it like this, maybe stuck the word or in, that would probably be okay as well. Just depends on the directions. So now, I'm ready for some adventures. I got a couple more equations over here that if you looked at, you'd say, not even sure where to get started. These ones, not too bad, requires a little bit of the quadratic effect, maybe, some kind of little factoring trick, maybe a substitution. But here, I got problems. I've got a sine of 3x and a sine of 1x in the same problem. I have a sum here of these two sines. Now, it wasn't that many sections ago that we had the following property. And I'm going to see if I can squeeze it in here. Well, I'll just write it below it here. See if I can remember. The sine of x plus the sine of y. This was a sum to product formula. It was 2 times the sine of, let's see if I remember this right, x plus y over 2 cosine x minus y over 2. I think that's the right one. You better go back and check for me there. Alright, so I'm going to make a substitution here. This is going to be my x, this is going to be my y. I'm going to rewrite this guy as 2 times the sine of 3x plus x divided by 2, that's 2x. And 3x minus x divided by 2, that's going to give me the cosine of 1x. Right. Equals 0. Well, it's not so bad now. What I'm going to do here is I have a sine of 2x, a cosine of x. I have these factors. I can set each one of these equal to 0, but you know what? I am going to replace the sine of 2x with 2 sine x cosine x using the double angle formula. So that gives me 4 sine x cosine squared x equals 0. I'm just avoiding that multiple of the variable there in that argument. So now this can be equal to 0, this can be equal to 0. So I have 4 sine x equals 0 or cosine squared x equals 0? Well, this is when the sine of x is equal to 0, and which is going to occur at 0 and at pi, also at 2 pi, but that's not part of my replacement set. And then over here, I take the square root of both sides. You pick up plus or minus 0. Well, that's just going to be the cosine of x is equal to 0. When does the cosine of x equal to 0? Well, that happens at pi over 2 and 3 pi over 2. Now, if you're wondering, well, I have trouble getting, somehow getting a 0 in the denominator like I did back here. Nope, because all of your functions don't have a variable in the denominator. So now you can go back and check. I'll just plug one in. Let's plug 3 pi over 2 in. The sine of 3 pi over 2 is -1. The sine of pi over 2 is +1. That equals 0. I think we can go through any of these, and I think we can get these to work out just fine. So I'm going to write the my solution set as 0 pi over 2 pi 3 pi over 2. And I list all 4 solutions. Now the last equation that I have on the board here is different from this one up here, because it's not like they have different arguments, is that they're different trig functions, and tangent and x do kind of pair up, because remember tangent squared x plus 1 is secant squared x, but that's not what I have here. I have tangent of x and secant of x both to the first power. That's going to be a problem. So on these kind, I mean, I can put everything in terms of sine and cosine and play around with it, but I think you're better off with this style problem to square both sides. Now, you have to be careful now, because if you square both sides, you have the ability, because the variables on both sides, of getting extraneous solutions. Definitely check your answers. So this is going to be tangent squared x plus 2 tangent x plus 1, and then over here I have secant squared x. Now I have a tangent squared x, I have a tangent x to the first power. The left side kind of looks like the quadratic appearance, the quadratic look, but not this guy. Here's where the trig substitution comes in. In for a secant squared, I'm going to put 1 plus tangent squared x. That's one of the Pythagorean substitutions. So now I have tangent squared x plus 2 tangent x plus 1 equals 1 plus tangent squared x. This is becoming interesting. If I subtract tangent squared x from both sides, it disappears. I'm not dividing, I'm subtracting. And if I subtract 1 from both sides, they disappear. I have 2 tangent x equals 0. The tangent of x is equal to 0. Well, when does the tangent of x equal to 0? Well, tangent sine over cosine. Tangent of x is the sine of x over the cosine of x. So that happens when the sine of x is equal to 0. And that happens at 0 and at pi. I definitely want to check my answers on this one. So if I plug 0 in, the tangent of 0 is 0 plus 1 is 1. So I have 1 here over on this side. The secant of 0, that's 1 over the cosine of 0, that's 1 over 1, that's 1. So I get a true statement. This is looking good. Well, let's try this guy, pi. The tangent of pi is 0, because it's the sine of pi over the cosine of pi, 0 over 1. Plus 1 is 1, the left side is 1. If I plug pi over here, the secant of pi is 1 over the cosine of pi, which would be 1 over -1, which is -1. 1 does not equal -1. I get to throw that out. My answer is 0, or the solution set contains 0. Now there's a little bit more that we have to do, but you're seeing some of the types of problems, trig equations, that come up most frequently, not only in pre-calculus, but also in calculus. So it's good for you to practice, practice, practice.